Hey everyone, this will be our first lecture in non-uniform circular motion and circular dynamics. The lecture video itself will be shorter than an hour and 20 minutes, but I will have points in the video where I will ask you to go answer questions in the Canvas quiz for this lecture, as well as try things on your own. So please pause the video accordingly and do those examples. Alright, so we'll start with a warm-up problem. This is a problem that's just practicing uniform circular motion. So go ahead and pause the video and figure out what the answer is going to be. And once you've done that, now I'll go through the problem with you. Okay, so the question asks, a small steel ball rolls counterclockwise around the inside of a stationary 30 centimeter diameter roulette wheel like the one shown in the image. The ball completes exactly 2 revolutions in 1.2 seconds. What's the ball's angular velocity? So, as you might remember, angular velocity is basically describing how many turns per second something does, but we conventionally in SI units give our result for angular velocity in radians per second, which you can tell from the units of the result. So in the numerator, we're basically plugging in how many radians we're doing. So 2 revolutions is basically 2 times 2 pi radians. So 2 revolutions, 1 revolution is 2 pi radians, so 2 revolutions will be 4 pi radians. And then that's going to be our numerator for the angular distance, basically, or the angle that the ball has traversed. And then in the denominator, we're dividing by how long that takes. So it takes 1.2 seconds. So 4 pi radians divided by 1.2 seconds. Let's calculate that. And we get 4.1 divided by 1.2. 10.47 radians per second. So 10.47 radians per second. So the closest answer for this would be 10 radians per second. All right. Next up, this is mostly a review of radial acceleration as well as tangential acceleration. So we talked about this back when we were just introducing non-uniform circular motion. So the radial acceleration of an object is the acceleration that keeps the particle going in a circle. It basically helps the particle change direction as it turns in a circle. And then the tangential direction is responsible for changing the speed of the particle. So if this thing is speeding up, it's going to have a tangential acceleration in the direction of velocity. And then if we're trying to slow down the particle, it would have a component of tangential acceleration opposite to the velocity. And the net acceleration is basically the sum of the radial acceleration and tangential acceleration. So if we do a r adding tangential acceleration to it, we get this is the net acceleration vector. All right, let's just review the tangential versus angular quantities for circular motion. The main punchline is basically the fact that angular values are same for all the points, and tangential values are not. They depend on how far out from the center of the circle we're located. So what do we mean by that? So we have tangential distance versus angular distance. So tangential distance is the distance as we move tangentially along the circle, which is the arc length. So the tangential distance is described by s, the arc length, and angular distance is described by theta. Now s actually depends on if you are close to the center of the circle versus far out on the circle. There's a different s1 versus s2. But theta for both of these, so from the center, the angle that these traverse is exactly the same. So it doesn't matter at what part of the circle that we are considering, the angular distance theta is the same. Next, for velocities, we have tangential velocity vt versus angular velocity, which is omega. So omega doesn't care if we're considering a particle in here or out here. Omega is the same for all of these. Basically, it's how many revolutions per second, or specifically radians per second, are we traversing. But velocity does care, because the particle on the inner circle is just traveling this distance in the same time that the particle on the outside is traveling a much longer distance. So their tangential velocity vt has to be greater than the tangential velocity of the particle in here. All right, and then the last set is the tangential acceleration, at, versus the angular acceleration, which is alpha. And the alpha for every spot on the circle that's going through circular motion is all the same. And then the tangential acceleration, the linear tangential acceleration is dependent on where along the circle you are. And all of these quantities are related as the following. So arc length is theta times r. If we take a time derivative of this equation, basically ds dt becomes your v, d theta dt becomes omega, and r is a constant. So vt becomes omega r, and then take another time derivative, v dv dt becomes a tangential, d omega dt is our alpha angular acceleration, and then r is constant. So these relationships are important for us to relate the tangential coordinates to angular coordinates, or the other way around. All right. Next, we're going to talk about the differences between and the similarities between uniform and non-uniform circular motion. So for uniform circular motion, which we did a fair amount of a few weeks ago, the linear speed v and the angular velocity omega are constant. So in uniform circular motion, the speed of the object is staying constant around the circle. In non-uniform, the linear speed v and the angular velocity omega are varying. For the angular and tangential acceleration, when we're in uniform circular motion, since the thing doesn't need to speed up or slow down, a sub t, the tangential acceleration, and the angular acceleration are both 0. On the other hand, if the thing needs to slow down or speed up, these are both quantities that are going to be non-zero. And remember, the relationship between at is just alpha r. All right, next, the radial acceleration. So for uniform circular motion, since the speed is staying the same, the radial acceleration is constant if you pick a point on your circle that's going through circular motion. On the other hand, the radial acceleration for non-uniform circular motion varies. Well, why does it vary? It's because v is constantly changing as you're speeding up or slowing down that particle. And then finally, the net acceleration for uniform is just a radial, because we don't have a tangential acceleration. But for non-uniform, it's the sum of both of those vectors, and when you add the radial acceleration and the tangential acceleration, they add in quadrature like this, and this gives us the net acceleration. And then finally, pretty much all of the motion of a particle around some path, a circular path in uniform circular motion, can be described like this, and let's just say plus some theta naught. So let's say you're starting at some initial angle, then where are you sometime later? Well, that's just where you start, plus omega t. And then for non-uniform circular motion, we need to use our kinematic equations from back in chapter 2 to describe non-uniform circular motion. So you might remember from chapter 2, when we first learned about linear kinematics, we became very familiar with these equations, both in 1D and 2D. So we had an x direction version of these equations, a y direction version of these equations. Now they're just written along some coordinate, let's say s. Well, there's an analog to each and every one of these equations in rotational kinematics. And how this analog works is the variable for displacement, which used to be x or y for us, and which is now s, basically is analogous to theta. And then velocity in the x direction, velocity in the y direction, or velocity sub s along some s coordinate is now analogous to the angular velocity omega. And then finally, the acceleration is analogous to the angular acceleration alpha. So these equations, just rewritten with their rotational analog variables, look very similar to the linear equations. And we're going to practice using some of these. So before we jump into that, let's just talk about sign conventions for rotational quantities. So far, we've talked about measuring displacement theta of some particle, let's say that's traveling along in a circular path. It also has some angular velocity omega and angular acceleration. And later on in this lecture and the next lecture, more in detail, we're going to talk about this quantity torque. So these are all quantities that require some sort of turning to describe their sign. So when the convention we usually follow for angles is, let's say I'm at some location here. Our general convention is starting from the positive x-axis, we go in the counterclockwise we go in the counterclockwise direction, and that's usually defined as some positive angle theta. Similarly, something that is turning in the counterclockwise direction in general is given a sign positive angular velocity, and something that's accelerating in the counterclockwise direction, that would be positive angular acceleration. So any direction for rotational quantities that is counterclockwise by convention, and this is totally arbitrary, but by convention in physics, we define this direction to be the positive direction. Also note, this is a little bit or not a little bit, this is completely dependent on whether you're looking at the situation from basically, so as I'm looking at my iPad as I record this, am I looking at it from the top of the iPad? Or on the other hand, I could look behind my iPad to the back of this. So to somebody who's looking on the back side of the iPad and viewing this turn here, that it might look clockwise to them. So we have to be very careful about what we call positive versus negative. We have to describe exactly from what perspective are we looking at the situation, and once you describe that perspective, there is some clockwise or counterclockwise sign that we put in. So, and things that are turning in the counterclockwise direction are considered positive, things that are turning in the clockwise direction are considered negative. This also, so if you take your fingers, so take your index finger, middle finger, and then the ring finger and pinky, and you just curl them in a counterclockwise direction, and when we can see each other in lecture, this will become more clear. Your thumb will point out of the page, and that corresponds to a positive counterclockwise turning variable. And then when you curl your fingers in a clockwise direction, your thumb would point into the page. So try that on your own, and we'll clarify this in the in-person lecture on Thursday. All right, here's another clicker question. Go ahead and pause this video and try it yourself.